So we were, I was showing you how to submit jobs through these batch scripts. So, yeah, I already showed you this. Where were we? Yeah, it should be this part. Okay, so I showed you yesterday a bit of a script directly in the terminal. So I think I should do that again, because this part is describing this, well, these directives that you need to put in the header of the script to allocate resources for your job, and then the rest of the script to basically execute your job. Besides the allocation of resources, the settings for the job, and then the execution. So I don't like very much this first example as a batch script. So let me show you some of the examples that we have in our documentation. Okay, so in our documentation, for example, if you go to using supercomputers, software stack, popular software, and OpenFOAM, which is a fluid dynamics tool that I use a lot. There is this section for specifically for OpenFOAM of example batch scripts on how to use OpenFOAM. So we can see here a more realistic example of a batch script. So what does it contain? It has the first line, which I told you yesterday is the shebang. In the presentation, instead of --login, it only has -l, which are exactly the same. And the idea is that first part, you are saying that this script is going to be interpreted by the bash shell in Linux, and then in Unix, and then that the script will start as if you were logging into the machine. So like clean environment. So the next part in this job scripts are the header of the several indications to the scheduler of what we need from the computer, and some other settings as how you want to name your job, for example. So then here again, you put my job, I want to give it a job name. Here is not set. It's just telling the users in the documentation that they need to set whatever name they want in these curly braces. So then the next part is where we want this job to be executed, and we are telling it, I want it in the work partition. And then some settings. These are really about the resources to be used. So it's just one task per node, and just one CPU per task. So this means this job is going to get just one core to be executed. I already told you we don't like this kind of jobs, but in the case of OpenFOAM, this part, if we read the title, is just a preparation for the real computational fluid dynamics simulation. So this preparation only uses one core, but it's not the real job. We will see the script for the job later. So then after describing what we need from the scheduler, then comes the script as a normal bash script. So the scheduler will assign those resources, which is one CPU, and also the memory In this case, if you need to set a different memory than the default, you need to set it here and the time. But if you don't set this --mem, then by default the scheduler will assign you the default memory for a single GPU, a single CPU, a single core. Okay, so after that, there comes the instructions for executing what I want to do in the script. In this case, I need to load the module of OpenFOAM. In this case, OpenFOAM or container version 7. Then OpenFOAM is ready to be used. Then some settings specifically for my job. In this case, I'm not going to go into details, but these are settings needed for OpenFOAM to work correctly. And what is very, very important, and I don't know if I stressed that yesterday, but really the piece in the script that is going to execute the job is these commands of srun. So srun is the launcher of the jobs. So we call each of these job steps, really. So the job has already been launched. You have some resources, but really it's not doing too much until you do the srun. So the srun is executing job steps, in this case, 3 job steps. And again, in srun, you can indicate again how many resources are to be used per job step. So in the past, Slurm used the approach that directly from the header, you decide how srun is going to run. Basically, like whatever you put in the header was going to be inherited by srun. So now one additional comment is this syntax is very short, just 1 letter per option. But these options are equivalent to the long options that are set via the --. So these are more clear, these are more concrete, and only if you already know what they mean, you will figure out what you are talking about. So in this case, capital N means 1 node, lowercase n means one task, and lowercase c mean the CPUs per task. So you can check that equivalency in our documentation or in the Slurm documentation directly online. So what I'm telling here is, I'm basically telling again that I'm going to use only 1 CPU in 1 node for this executable. So this block mesh is finally the OpenFOAM executable. In this case, this one is created a mesh, this one is setting something about the mesh, and this other one is decomposing the mesh into several pieces. But basically, this is a more complete job script. Now, let me show you the one for the solver, and I can do a demo on how to run it. So the one for the solver is a bit more complex in terms of what I'm asking for. So again, the shebang, then I give it a name. Again, this one is going to be a CPU only in the work partition. And this one is using now a large amount of tasks. In this case, 1,152 tasks. And I'm telling that 128 per node. So basically, I'm filling nodes up to the number of tasks that I need for the job. So in this decomposition of the mesh, it was a pre-step, and what happened in this case is the mesh is decomposing 1,152 parts that are going to be used by the solver. 1 CPU per task. And this directive is important, the exclusive. So we are telling that basically all the resources in each of the nodes assigned are going to be exclusive for this job. Nobody else can run a job in the nodes assigned. So basically, give me all the resources of the nodes. Once that is set, I start my script saying I'm going to use this version of OpenFOAM, then some OpenFOAM settings, and then finally the execution of the solver. Here is just a single job step with srun. And again, I'm saying I'm going to use a certain number of nodes. And Slurm should already, after the allocation of your resources, set an environment variable with the number of nodes that are going to be used. So I'm saying I'm going to use the number of nodes that Slurm already calculated for this srun. I'm going to use the number of tasks that are clearly defined here for this srun, and I'm going to use only 1 CPU per task again. So this is a bit of repetitive. As I said previously, Slurm was trying to avoid all this repetitiveness. So basically, if you see the slides, you will see that in our examples, we are only putting srun and the executable and not repeating these kind of settings. But Slurm is moving towards a different approach that you tell in the header what resources you want, and you clearly specify in your srun what are you going to run. So this is more in agreement to where Slurm is moving towards. Some settings for getting some resources, and then again, some settings for running each of your job steps. So we need to get used to this. So PimpleFoam is the OpenFOAM executable, and this is a parameter for the executable. This is not part of Slurm. So these two words are pure OpenFOAM, and all these are Slurm. Okay. And the way to run it is by submitting this job script through an sbatch command directly in your terminal when you are connected to Cetonix. So let me show you that. Okay, so I'm here already in one folder where I have what is happening? A similar script. So that script is the run foam. So basically you just do sbatch run foam.sh. And then that job has been submitted. It has been assigned a job ID. So I can check what is happening with it with the sq --me. So it is looking for resources. Now it is running. And the output is in this Slurm dash and the number of the ID. So this job will take a few minutes to run. And this is not on the slide, so you can take note that you can basically see the output file. How is it progressing? If you do a tail command, then -f and the name of the file. So if you do that, you can see the output that is being written to the output file and how is it progressing. So this job is running. These are indications of OpenFOAM itself doing the fluid dynamic simulation. etc. So to get out of this command, you do Control-C. Control-C. And then I'm out. So the tail command is a command to visualize text files, but if you do the tail -F, it will keep you showing the end of the file, the tail of the file continuously. Okay, so we can leave that job running, or we can basically practice, and I can cancel it. sq-me, and then I don't need that job anymore. Let's cancel the job ID. Now the job should appear in this is not a running status. It is being sort of doing the final steps after the cancellation, and the job is not there anymore. Okay, so I guess I can ask here for questions. Do you have any question? Okay, I see. Do you need to specify a host file? A host file. What is a host file?
Shell script and specify the srun. Do you need to specify a host file or inside sbatch? Like the node already knows which nodes to connect to, or
yeah, okay. So if I understand correctly, you're saying,
oh yeah, in that line when you do srun.
Yeah, if we need to give srun some instruction to where to run. No. So it is srun is running inside the allocation. So basically, if you see, we are not telling here the name of the node, but we are telling in which partition we want to run. So in the header, so this header is interpreted by Slurm. So once we do, yeah. So the submission command was sbatch and then the name of the script. So this is the script. So once we do the sbatch and the name of the script, that script goes directly to the scheduler, and the scheduler checks all these hash sbatch pieces in the header and interprets them accordingly. So the scheduler receives this and says, okay, somebody wants to do a job named whatever. Somebody wants to do that this job goes to the work partition, okay, and wants to use this number of tasks in that work partition, okay, and then the scheduler checks, okay, this work partition has this many resources available, or it doesn't have resources available, and I need to run, I don't know, these 900 jobs that were already submitted before this one, so I know how I'm going to use the resources, and I estimate that this new job may be able to run probably at 5 p.m. in these nodes. So the scheduler checks and assigns where specifically it's going to run. Then it stays in the queue until the resources are available, and then the job starts. Then it passes to this first line, loads a module, goes through this, and srun will run inside that allocation. So for srun, you don't need to tell anything in terms of where.
Yeah.
You don't need to tell anything in terms of where. You only need to retell in srun of the resources that were allocated.
Okay.
What are you going to use in this job step?
Yeah.
And then the executable. Okay.
Mm-hmm. So without srun, so say I've got a command like a shell script or a command, the command is just going to run a single like node or single process without srun.
Exactly. So all these are commands, and you don't need to use srun. and they are going to be running in the if I can say in the master core of this 1000. There is a master core that is in charge to execute these pieces. Yeah.
Yeah. How about for the case of running a Python file? Say like on the last line, I want to run a Python file that uses multiprocess. Do I still need to run it through srun, or it's being done internally on Python process and the code?
Yeah, you need to use srun.
Like
So,
even for those Python, yeah, sure.
Yeah, so yeah, I'm not super savvy in Python. We can confirm that later with Pascal, but
yeah,
you
sure.
need to use srun. If not, it's going to be using just a single just your single core in the master core.
Yeah, thanks. Oh,
But
wait, just to clarify on top of that. So say like, let's not use example Python. Say that the program has MPI code inside and want to run distributed computing. Even in that case, do you still need to do srun? Because I thought srun runs MPI inside that. So I just wondering if you can replace that with just MPI run and stuff.
Yeah, the MPI run and srun are sort of equivalent. So they are launchers.
Okay, yeah.
They are
Okay.
the launchers of the tasks. So
Yeah.
that's a very good point, and we need to clarify that I think better in the slides than in my explanation.
Thanks.
So for those that are used to run MPI jobs, so srun is equivalent to the MPI run or the MPI exec. But you cannot use MPI run or MPI exec here in these scripts. It's going to not do whatever you want or not even run. So the one that really makes use of the resources that are available to you in the job is srun. And yeah, I have seen many codes that have their own scripts or their own series of scripts, and they have the MPI exec within those scripts to run anywhere else. If you have one of those, you will need to go and edit the scripts and change the MPI exec for sruns and whatever other adaptation you need to do, for example, to catch this kind of parameters for the srun command.
Yeah, thank you.
Cool. Any other questions? Okay. So let's go back to the presentation and see some other of information that is there. So in the presentation, there is more detailed explanation of what each of these mean. So we already cover job name. So this account is important. I was not using it. So if you are in different projects, then you need to tell which account this job is going to be charged. Remember that every project has been given a certain amount of service units, and those are consumed. So basically, you need to tell on which project to charge the job, which partition to use, time, and this QoS is the quality of service. If you remember yesterday, we saw that there is a normal, there is a high priority. So you can use the high only for 10% of the allocation for your project, and whenever you use high, your job will get a higher priority and will basically go through faster than normal. Okay, and here, if you see, there is not all the list of the srun parameters. The only one that I'm adding here, and that might be different from the slides you have because I did this morning, is the -c. And this is because -c, which is the correspondent to the CPUs per task, because Slurm, as I told you, Slurm already started to change, and in the future, it's not going to inherit everything from the header. And this one is already not being inherited. So this one, today, we are forced to put it explicitly. So in this case, I'm doing this, repeating whatever I want for the number of CPUs per task in the srun. So now these are the more important ones, because with this, Slurm basically will calculate the resources. So n tasks is the number of tasks that you want to execute. It's totally related to the MPI concept of tasks. And basically, if you don't set it, it's going to think it's going to look for only one task. But yeah, you need to set how many tasks. And if you say how many tasks per node, with these two, you can calculate the number of nodes that Slurm is going to look for. There is this other sbatch parameter. So you can do sbatch, you can do hash sbatch dash dash nodes equal and the number of nodes you want. So that's another option. So there are, I don't know, in this case, there are so many parameters for Slurm. If you go to the documentation, you will see that many parameters. So there are, I would say, infinite combinations for Slurm to then calculate which are the resources. But these are the more basic and typical to use. So with these two, basically you are setting how many nodes. Well, with the three, because then we say how many CPUs per task we're going to use. So with these three, you basically set the number of resources. And now on Cetonix, we only have 128 cores available. So the number of tasks per node times the CPUs per task should not exceed 128. And CPUs per task is a setting totally related to the OpenMP parallel programming style. Yeah. What else? The mem. So you can also tell how much memory you need for your job. So sometimes, for example, in these kind of jobs that we are only saying 111, the amount of memory is just 128. So the total memory available is divided in 128 pieces, and only one of those pieces is assigned to the job. So that job is prone to have shortage of memory. So if you need more memory, you need to tell it with the dash dash mem parameter. So you just basically put, for example, if you need 56 gigabytes, you write 56G. I think there is something about that later in the slides. Okay, so let me go first for this another example that is dealing with the exclusive option. So besides all those settings, if you add the dash dash exclusive, again, this thing is telling that you are going to, or you are asking for the whole resources in the node. And you will be charged for the whole resources in the node, even if you don't use them. For example, if you say exclusive, and then in srun you set srun -1 -n1 -lower n1 -c1, like using just a little piece instead of the whole node for that job step, and that is being only executed like that, then you will still be charged for the whole resources that are allocated, not the ones used in the job step. And if you don't need whole nodes for your job, you basically use the normal approach, but these two extra options are best practice that we are suggesting, especially the distribution block thing. So the point is, this is very sort of like I'm just giving you the formula without explaining too much what that means. But the idea is that the resources that are going to be allocated are going to be packed within the node together. So the idea is all the memory and the cores are together within the chips in the node to allow the rest of the node be free and be useful for other jobs that also will be packed together in little pieces within the available resources in the node. The end tasks per socket, so the sockets for the CPU nodes are the chips themselves. So the two CPUs, so of 64 cores each, are the two sockets available in each of the nodes. So for example, if you are using only less than 64 cores, it is a good practice to say that you are going to use all those 64 in a single socket. Okay. What else? Tips. Improve batch script reproducibility. Always specify the partition, the number of tasks, and the number of tasks per node. Okay, and also don't go for it like in the very first time. So it is a good idea to go step by step and send some test runs to see if everything is okay before you say, okay, run for 24 hours this job in 1,000 nodes. You need to be very sure that that is okay with pre-testing your code and pre-testing your settings, etc. Okay, so this slide is just for telling you that you can also run several steps. Once you have an allocation, you can run srun with different number of settings from the header, as long as these resources that you are asking in the srun are available. So you cannot exceed them, but you can use less, and you can run several steps there. Here it says without options, srun will use resources as defined via the sbatch directives in the header. And I just added this part except for the CPUs per task option. That is not inherited. You can check that in the Slurm documentation. Okay, so quickly, some examples of when the job is exclusive is using all the resources of the node. We're marking them as P with the tasks as P. I don't know what P means. Processes in this slide equivalent to task. In this case, this one is an OpenMP kind of code. So this one is asking just for one task per node, but 128 CPUs per tasks. And then these are some OpenMP settings. The most important is the number of threads, the number of OMP threads. And we are here assigning the number of OMP threads equal to this environment variable. So this environment variable is taken from the allocation, although it's not inherited towards the srun. Anyway, so but the 128 is set into this environment variable because after the header is interpreted by the Slurm. And you can grab that 128 and assign it to the OpenMP variable. This is for OpenMP to work correctly and for telling OpenMP that you are going to use 128 threads in the OpenMP code. So here you can use, rather than the 128, you can use again this environment variable as this, or you can use $OMP num threads because this one also already has the 128, whatever you prefer. If you remember the OpenMP script that I showed you before, rather than using numbers in these settings for this run, I was using this kind of environment variables. Now again, you can check that in our documentation. And in the schematics of the node, this is the only task that that is going to be executed in the master core, and then the 128 threads are being executed from this master thread to the rest of the cores available in the node via OpenMP. These other are OpenMP settings that I'm not going to touch at this point. This is another example saying that I'm going to do 2 tasks per node and 64 CPUs per tasks. That means 64 OpenMP threads per task, but 2 tasks per node. So this is the node. These are the 2 tasks that are being assigned, and these are the 64, each of them having the 64 threads working together with the master thread here in OpenMP. Okay, this is an example of not using full nodes. Yeah, this one was using saying exclusive. Even if the exclusive was not there, with the settings told here 128 or 64, but 2 tasks per node, we are filling the node. But in this one, we are not filling the node. So let's say this one is only doing 64 tasks in the style of MPI, 64 tasks per node, and we are telling 64 tasks per socket. So we are telling everything to be done in a single socket or in a single CPU with 64 cores. Again, this is important to tell Slurm that Slurm needs to assign everything for this job all packed together. And then this is the way the allocation of resources is done. In this case, we are not asking for the whole node. We are not putting exclusive, and these settings are only asking for 64 cores. So you are not going to be charged for the whole node, only be charged for this partial use of the node because you are not asking for it. So this is your charge. This is your assignment. Your job will run only here. This is a space available for other jobs to run. Another example, this one is being assigned through the memory. So you are saying only 1 task per node, only 1 task per socket, all pack, only packing 1, but anyway. But then, well, I guess this is important because you are asking for more memory than the default for a single task. So you are asking for 64 Gs, which is equivalent to 32 cores, or a quarter of the available memory. So you only have 1 core to execute your job, but all this space is going to be sort of blocked for other jobs to run. That's because you're asking for 58 gigabytes of memory, which is 1/4 of the node. So you will be charged for all these anyway, even if it's just one task. And that's because you are using the equivalent in memory of a quarter of the node. So basically, we are charging for the proportion of the node being used. Can be the proportion in memory or can be the proportion in cores. In this case, is the proportion of memory.